Now, and in the one of the earlier videos, I have given you certain expressions connecting various thermodynamic parameters. Here, since we have the Q also over here, let me update on that. You can make similar updations on your notebook also. So basically now what I write down is I can write U average energy. U is equal to minus of dou by dou beta ln Q. That's one expression. A expression, A is the Helmholtz free energy. You know its expression already. A is equal to minus kT ln Q. We have derived this expression in one of our previous videos. And then there are, so the moment you know the A, so as I told earlier in one of the earlier classes, the point is that for every system, every canonical ensemble system, one can evaluate or derive the expression for partition function Q. And that's a fingerprint information for a system, statistical fingerprint. And the moment you have the partition function, one can calculate the Helmholtz free energy. So now if I can connect this Helmholtz free energy with various other thermodynamic parameters, now I can, the moment I know the Q, I will be able to calculate all the other thermodynamic parameters. So let me write down certain expressions here. The pressure P is equal to minus dou A by dou V. Entropy S is equal to minus dou A by dou T. So these are all expressions which we might have mentioned in our earlier videos. Mu is equal to minus dou A by dou N, and specify it at constant volume, Cv is equal to minus T into dou squared A by dou T squared, and specify it at constant pressure, Cp is equal to dou H by dou T. So I don't have the H here, but H is equal to what? H is equal to U plus PV. So if you need to calculate the enthalpy H, H is equal to U plus PV. So I have the expression for the U, the P, and so therefore I can calculate the Cp also. So Cp is equal to dou H by dou T. Cv is equal to minus T dou squared A by dou T squared. Okay. Now what I will do is that I will try to evaluate an expression for A of the system. So basically now I will ask you to, since we have the Q here, now it's a simple thing or it's a routine thing for where you can take that Q, put the Q over here, and you calculate the Helmholtz free energy A of the system. So this is purely now a mathematical solving thing. But for a beginning, let me do that over here, an expression for A. So what was that? A is equal to minus kT ln Q, and I know the expression for the Q of the system also, minus kT ln 1 by n factorial V by h cube raised to n 2 pi mkt raised to 3n by 2. Right? I have just simplified by taking the n inside, so to help me for this applying the logarithm. So I can write down that expression as minus kT ln V by h cube raised to n 2 pi mkt raised to 3n by 2 minus, right, I have to apply the logarithm here also, minus ln n factorial, right. So this is one way I can write, and now I can apply the Stirling's formula for the ln of n factorial, and I try to simplify that. So ln n factorial will become n ln n minus n. So assume that you have instead of ln n factorial, you put that over here, and then I can write the expression modify the expression as minus nkt ln v into 2 pi mkt raised to 3 by 2 divided by h cube minus ln n. Basically I have taken the n outside. Then I will reach to something like this. And of course, instead of this negative thing, I reverse the ln and I can adjust this as nkt ln n by v that's squared by 2 pi mkt raised to 3 by 2 minus 1. I've taken the ln of n also inside or here, and then we can write something like this. One can always go on simplifying the expression, but this is one simple point at which I think I should stop that. So this is again what? Lambda h by 2 pi mkt raised to h by root of 2 pi mkt. So this I can always express it in terms of lambda also, right? You can write down in this expression in terms of lambda also. Okay, so the moment you have the lambda, I stop there. You can always go on simplifying that depending on the if the expression is to prove that something. So you have to always do the your mathematical adjustments according to the need. Now let me write down some of the final expressions which you should be getting when you are using this set of equations for the kind of partition function we evaluated. So mu is equal to kt ln n by v squared by 2 pi mkt is 3 by 2. P which is the minus dou a by dou v, and I should be getting nkt by v. That's why, because this is a classical ideal gas, right? So this is the expression I should PV is equal to nkt I should be getting. So you can try to get that expression, and S is equal to minus dou a by dou t which will turn out to be nk ln V by N 2 pi m kt by s squared raised to 3 by 2 plus 5 by 2, right? And U is equal to 3 by 2 n kt, the average energy of a classical ideal gas. So these are all standard expressions which you must have done in your earlier classes. So but through this route also we should end up getting this one. And CV is equal to what? CV is of course then CV is equal to 3 by 2 nk, and Cp is equal to 5 by 2 nk, right? So these are the kind of expressions which we need to calculate, which you people can do it yourself to find out these expressions. Okay, that's it.